Within the BSS, the user and signaling data is transported over a series of interfaces. The A interface connects the Mobile Services Switching Center, MSC, with the Transcoder TC. The A-ter interface connects the transcoder with the Base Station Controller, BSC. The A-bis interface connects the BSC with the Base Transceiver Station, BTS. Finally, the data is transmitted to the mobile station via the air interface, UM. Let's consider the PCM30 configuration as an example for the frame structure of data transmission between the MSC and the mobile station, to understand the data flow at the A interface, the A-ter, A-bis and UM interfaces. We see that the 4 A links are mapped onto one A-ter link. 4 A channels of 64 kilobits per second each are mapped onto an A-ter channel consisting of 4 subchannels of 16 kilobits per second each. In total, the 128 channels of 4 A links are reduced to the 32 channels of one A-ter link, which are numbered consecutively from 0 to 31. The Ss7 signaling, which in our example is to be found in time slot number 16, is transmitted from A to A-ter transparently. That means unchanged. The frame structure consisting of 32 channels is also found at the A-bis interface. Channel 0 is used for synchronization. The remaining 31 channels transmit warning information for operation and maintenance of the BTS, known as O&M alarms, as well as signaling and voice data. Finally, the information from A-bis is transmitted to the air interface UM via the TRXs, the radio transceivers of the BTS. 2 A-bis channels of 4 subchannels each correspond exactly to the 8 time slots of a TDMA frame, which carries the data to the mobile station. A TDMA frame, which we'll discuss in more detail later in the course, portions the stream of physical channels or time slots on a particular carrier frequency into periods. Its time slots are numbered consecutively from 0 to 7 and can be assigned to one TRX. The A interface transmits user and signaling data between the MSC and the transcoder. It's the second completely standardized interface in GSM after the air interface. As an open interface, it's not tied to a specific producer. The A interface is an ISDN S2M interface that's been adjusted to GSM with a data rate of 64 kilobits per second per time slot. In the PCM30 configuration, the A interface contains 30 traffic channels. Time slot number 0 takes over synchronization tasks, and time slot number 16 contains signaling information in the number 7 signaling system format, or Ss7. Thus, the air interface has an overall bit rate of 2048 kilobits per second. The PCM24 configuration, which is generally used in the USA, uses 24 traffic channels. In both configurations, each frame has clearly defined channels for signaling and synchronization information. 4 traffic channels of the A interface are bundled into 4 A-ter channels of 16 kilobits per second each, which are subsequently transmitted to the BSC in a 64 kilobits per second physical A-ter time slot. Conversely, signals coming from the BSC are transcoded from 16 to 64 kilobits per second, which is the bit rate typically used in fixed networks. Signaling channels are not transcoded. At the A-ter interface, 120 speech channels of 16 kilobits per second each form a 2 megabit per second multiplex connection. 4 times as many A links as A-ter links are necessary to transmit the same amount of voice data. Now let's turn to a procedure which takes the original speech and generates the speech description parameters in the TC. During the first phase of GSM, which lasted until 1995, A speech codec in the MS and in the transcoder was specified as the full-rate codec. The basic characteristics of speech, that is the volume, the base frequency and the tone, are extracted in 20 millisecond segments from the 64 kilobit per second signal, so that descriptive parameters in 16 kilobits per second signals are generated. The prediction algorithms, that is to say, the calculability of speech, make the data less sensitive to the interference a signal meets on its way from and to the mobile station at the air interface. In GSM, all voice signals are transmitted the same way and in a continuous data stream. The channel is occupied even during silence intervals. This has two fundamental disadvantages. Firstly, since the mobile station must send for the whole duration of the call, transmitting power is used even in silence intervals. That means when the subscriber is only listening. This wastes the mobile station's battery power. Secondly, other subscribers using the same frequency in distant cells could be disturbed more than necessary. Therefore, it's logical to switch off the sender whenever the subscriber is not actively transmitting information. Considering the pauses in the dialogue and also the pauses between and within the sentences, we find that the average occupation of the radio link is less than 40%. Discontinuous transmission, or DTX, is a remedy to this problem. In DTX, a function known as voice activity detection switches off the sender of a mobile station whenever there's no data to be transmitted. During speech pauses, a stop gap in the receiver, which in the uplink is the corresponding transcoder element in the TC, must simulate a functioning channel for the user. In GSM, this is called comfort noise. It's the background noise analyzed before the MS is switched off, regenerated by the TC. The comfort noise is even updated during a speech pause by the mobile station transmitting relevant information to the TC. The A-bis interface connects the Base Transceiver Station, BTS, with the base station controller, BSC. In the PCM30 configuration, the data at this interface is transmitted via cable or via microwave transmission at a bit rate of 2 megabits per second. A cable connection is more resistant to interference, but a network operator must lease it from a fixed network operator. The microwave links can be operated independently and are easily configured by the network operator, but they are more sensitive to interference. 4 types of information can be transmitted over the A-bis interface: user information, synchronization data, signaling information, and data for the operation and maintenance of the BTS, known as O&M alarms. In the basic configuration, the channels of the A-bis interface are directly connected to the time slots of the radio transmission at the air interface. The physical data rate is 64 kilobits per second. In PCM30, time slot 0 of the A-bis interface is used for synchronization. The remaining 31 time slots of the PCM30 configuration carry data from and to the transceivers of the BTS, as well as signaling information and O&M alarms. In the uplink, 4 traffic channels of 16 kilobits per second each are submultiplexed and transmitted from the BTS to the BSC in a physical A-bis time slot. The same happens in the downlink, only in the opposite direction, that is, from the BSC to the transceivers of the BTS. Today's BSC-BTS connection can also be configured as a dynamic link, with variable signaling and traffic time slots, according to the current traffic situation. Two PCM30 channels can be assigned to one TRX. These channels consist of 4 sub-time slots each. Each PCM30 sub-time slot corresponds to a time slot in the TRX. Thus, by mapping 8 PCM30 sub-time slots onto one TDMA frame consisting of time slots 0 to 7, the entire TDMA frame of the TRX would theoretically be available for the transmission of payload data. But then, there wouldn't be enough space left for the necessary signalling traffic from and to the mobile stations. According to a fixed producer and configuration-specific pattern, the signalling information is carried in specific A-bis time slots of 64 kilobits per second each, or in 16 kilobit per second sub-time slots, to at least one TRX per cell, where it uses time slot 0 to be transmitted over the air interface. Special time slots carry the O&M alarm traffic between the OMC and the BTS over the BSC. The information is, of course, not transmitted over the air interface. As we could see at the A-ter interface, each 16 kilobits per second of a traffic channel consists of 13 kilobits per second of payload and 3 of in-band signaling between the BTS and the transcoder. Only the 13 kilobits per second of payload data may be transmitted over the air interface. Depending on the producer and on the configuration, each A-bis connection in the PCM30 configuration may transport user information, signaling information, and O&M information from and to up to 15 transceivers. In the PCM24 configuration, 24 channels achieve an overall bit rate of 1536 kilobits per second at the A-bis interface. Up to 10 transceivers can be assigned to a connection. Let's summarize what we've learned about the three terrestrial interfaces A, A-ter and A-bis. Each of these three interfaces transmits information for the synchronization of the individual network elements point to point at a data rate of 64 kilobits per second and using time slot 0. The transcoder merely forwards the Ss7 signaling between the MSC and the BSC. This is done transparently at a bit rate of 64 kilobits per second, both over the A and over the A-ter interface, for example in time slot 16. The TRX-related signaling between the BSC and the BTS is transmitted over the A-bis interface at 16, 32 or 64 kilobits per second depending on the producer. O&M alarms from the transcoder are transmitted to the BSC over the A-ter interface at 16 kilobits per second or as in-band signals through a normal traffic channel. O&M alarms from the BTS are transmitted to the BSC, which is also the O&M master for the entire BSS, over the A-bis interface at 16 or at 64 kilobits per second. If the BSC is unable to correct the errors that cause the alarms, or if it detects an error within itself, it informs the OMC directly, or forwards the alarms from the BTS or TC to it. Let's consider the transmission of speech and user data, which is transmitted at a data rate of 64 kilobits per second over the A interface, at 16 kilobits per second over the A-ter interface after being turned into transcoded speech or rate-adapted data, and also at 16 kilobits per second per sub-channel over the A-bis interface. SMS messages are transmitted via signaling channels. The number of physical time slots that's available for the transmission of signaling information over the air interface depends on the configuration and is up to the manufacturer or to the operator. Within mobile radio networks, data is transmitted over PCM lines at a bit rate of 2 megabits per second. Air transmission is used between the mobile station and the BTS, and the information transmitted over the air interface must be adjusted to the PCM line so it can pass through the rest of the network. The air interface, or UM, is the weakest part of a radio link. In GSM, a lot is done to ensure high quality, security and reliability. At the air interface, the frequencies are arranged in pairs. Each uplink frequency has a downlink frequency permanently assigned to it. The uplink signal goes from the mobile station to the base station, and the downlink signal goes in the opposite direction, from the base station to the mobile. The arrangement in pairs is what actually enables simultaneous communication. The difference between the frequency pair is fixed and is called duplex frequency. In GSM 900, the duplex frequency is 45 MHz. Accordingly, the uplink frequency range, 890 to 915 MHz, is assigned to a frequency range of 935 to 960 MHz in the downlink. In GSM 1800, the duplex frequency is 95 MHz. The uplink frequency range lies between 1710 and 1785 MHz. The downlink frequency range between 1805 and 1880 MHz. In GSM 1900, the duplex frequency is 80 MHz. The uplink frequency lies between 1850 and 1910 MHz, and the downlink frequency between 1930 and 1990 MHz. The BTS elements which send and receive radio signals in the downlink and uplink channels are known as transmitter and receivers, or transceivers, TRX for short. In GSM networks, the transmission over the air interface is digital. Digital transmission in GSM is based on a combination of the FDMA and the TDMA methods, which already have been introduced. In frequency division multiple access, or FDMA, different frequency channels are assigned to each BTS. Mobile phones in neighbouring cells or within the same cell can be used simultaneously but occupy different frequencies. The FDMA method uses different carrier frequencies: 124 in GSM 900, 374 in GSM 1800, and 299 in GSM 1900. Time division multiple access, or TDMA, is a method where several subscribers share one frequency. Each subscriber is assigned its own time unit, which is known as a time slot. In analog mobile systems, on the other hand, a frequency is occupied by one subscriber for the duration of the call. In TDMA systems, each mobile station sends and receives information only on the time slot it's been assigned. These time slots are either used to transmit voice data or information on signaling and synchronization. To send digital information over the air interface, the analog radio signals must be interpreted as bit signals. In this process, the transmission of digital information to the air interface is called modulation. Modulation takes advantage of the physical characteristics of analog signals and changes them in a certain way, depending whether the digital value to be transmitted is 1 or 0. Signals can be modulated on the basis of their amplitude, their frequency, or their phase. GSM uses a specific phase modulation known as the Gaussian minimum shift keying, or GMSK. Time division multiple access, or TDMA, splits a radio frequency into consecutive periods known as TDMA frames. A TDMA frame, in turn, consists of 8 short time units, which are referred to as time slots. These time slots represent the physical basis for data transmission. Therefore, they are also called physical channels. The radio signal between the mobile station and the BTS consists of a continuous stream of time slots organized in TDMA frames. Each connection is always assigned one time slot. Thus, the physical channels provide the resources used to transmit specific types of information. The types of information and the functions define logical channels. Logical channels differ according to their function they fulfill in data transmission. To organize the radio transmission, various frame types consisting of numbered time slots are specified in GSM. The numbered time slots are continuously numbered off by the mobile station. A simple TDMA frame consists of 8 physical channels, or time slots. A time slot is 0.557 milliseconds long. Thus, a simple TDMA frame is 4.62 milliseconds long. The length of a time slot is also referred to as the burst period. A burst is the content of a physical channel. Information is transmitted as bursts each TDMA frame period. Traffic channels, that is, time slots 0 to 7 in a basic TRX configuration, contain their information organized in 26 TDMA periods of time known as a multiframe. This is 26 times 4.62 milliseconds, in other words, 120 milliseconds long. Signaling information, normally provided in time slot 0, is organized in 51 TDMA periods of 4.62 milliseconds each, which makes 235 milliseconds altogether. 26 of these long 51 multiframes, or 51 of the short 26 multiframes, form a superframe, which is 6.12 seconds. The largest transmission unit defined is the hyperframe, which contains 2,048 superframes and is 3 hours, 28 minutes, 53 seconds and 760 milliseconds long. TDMA frames, multiframes, superframes and the hyperframe can be considered as counters to organize user and signaling information within the TRX and to support ciphering at the air interface. The information which is physically transmitted over the air interface UM via the physical channels must be converted into a 16 kilobit per second signal within a 2 megabit per second frame, which connects the BTS and the BSC as the A-bis interface. It's very important that all mobile stations within a cell send their digital information at the right moment, in order to avoid collisions at the time slots of the air interface, which would destroy the transmitted information. Therefore, each mobile station sends its digital voice data at regular periodic intervals, using a different time slot to the other mobile stations within the same cell. The medium for this transmission process is the time slots or physical channels. The content of such a channel is also known as a burst. Bursts consists of different data blocks containing payload as well as security information to guarantee high data reliability and transmission quality. In GSM, there are two types of logical channels: the dedicated channels and the common channels. Let's explain the difference between the two with a metaphor from gardening. If we want to water a whole area, and not a particular plant in it, we use a watering can. This metaphor describes the common channels. These supply their data according to the principle of equal shares for all, and are not directed to a specific target. They're used to broadcast information area-wide to all the mobile stations within the service area of a BTS. This is general signaling information, for example, to log on to the network and cell broadcast SMS. If, on the other hand, we only want to water a specific plant and deliberately leave out the neighbouring ones, we use a jet of water. This metaphor corresponds to the dedicated channels. These are always directed to a particular addressee. Various types of signaling channels, known as the dedicated control channels, facilitate communication between the mobile station and the mobile radio network. And of course, traffic channels that carry user speech and data also belong to this category. To understand the tasks of the individual logical channels, we'll now look at how a mobile station logs on to the network. After the subscriber has switched on his mobile station and typed in his PIN code, the mobile station searches for a network. But how does it log on to the network the subscriber is registered with? For this purpose, the BTS sends out the frequency correction channel, FCCH, at short, regular intervals. to help the mobile station find a frequency for downlink reception and adjust its frequency oscillator for the uplink transmission. To do so, it picks out the strongest received signal. The synchronization channel, SCH, then helps the mobile station to synchronize itself to time slot 0 sent out by the BTS. This means the mobile station must adjust to the rhythm given by the BTS. The SCH contains the TDMA frame number as well as the base station identity code, containing basic information about the network operator that can be compared with the info stored on the SIM card. After this step, the mobile is able to decide whether it's chosen the proper network. If not, it starts the same procedure again, trying with the second strongest FCCH received. While the mobile station uses the FCCH to adjust its frequency, and the SCH for synchronization and network identification, the broadcast control channel, BCCH, which is also sent by the BTS, supplies the mobile station with additional information about the selected cell, for example, for ciphering. For some value-added services, for example, location-dependent services, additional information has to be transmitted from the BTS to the mobile. The cell broadcast channel, CBCH, is used for this purpose to transmit geographical parameters, for example the Gauss-Kruger coordinates of the BTS, to the mobile. The FCCH, SCH, BCCH and CBCH are broadcast channels and exist only in the downlink. They are the first logical channels belonging to the common channels. The mobile station has now adjusted its frequency and synchronized its TDMAs and has picked out the best cell available. But before it can be reached by other subscribers and before it can initiate calls, a location update and authentication procedure are necessary. Only after that is the mobile station logged onto the network and has radio coverage. It can now be reached by other mobile stations or initiate a call. For this purpose, common control channels are required. Common control channels are point-to-multipoint channels, which exist either only in the uplink or only in the downlink. When a subscriber is called, the paging channel, PCH, is broadcast in the downlink by all base stations within a location area, so that the mobile station concerned can react. To initiate a call, the mobile station sends out a random access channel, RACH, which carries its identification and request, for example, for registration to the network. This channel only exists in the uplink. In return, the network sends the access grant channel, AGCH, in the downlink direction to assign resources to the mobile station by granting it a stand-alone dedicated control channel, SDCCH. The PCH, RACH and AGCH form the group of the common control channels belonging also to the common channels. A stand-alone dedicated control channel, SDCCH, has to be assigned to the mobile station to exchange the requested signaling with the network, for example, authentication, ciphering or call setup. Also, it assigns a traffic channel and it transmits short messages. The SACCH is always linked with an SDCCH or a traffic channel. It sends measurement reports to the network and is used for power control and to handle the exact temporal alignment of the channels, the so-called timing advance. If the subscriber moves into the service area of another BTS, the handover command needed is transmitted over the FACCH. This channel is also used for every call release. During the call, FACCH data is transported over the traffic channel assigned. the dedicated control channels are bidirectional point-to-point channels and belong to the group of dedicated channels. User speech and data are transmitted over the traffic channels we've already spoken about. Traffic channels are bidirectional and also belong to the group of dedicated channels. There are two different channel types supporting different gross bit rates. The traffic channel full rate, TCHF, has a gross bit rate of 22.8 kilobits per second. It's used for speech, encoded by a full rate or enhanced full rate codec, as well as for user data, encapsulating a net bit rate of 9.6 kilobits per second for standard bearer services, 14.4 kilobits per second per time slot in the case of HSCSD, or up to 21.4 kilobits per second with GPRS. The traffic channel half rate, TCHH, supports 11.4 kilobits per second and is only used for half rate codec speech. Let's sum up what we just learned about the classification of logical channels. Common channels include FCCH, SCH, BCCH, PCH, RACH, AGCH and finally CBCH. All contain point-to-multipoint signaling information. Dedicated channels contain point-to-point signaling, such as SDCCH, SACCH and FACCH, or traffic, such as TCHF and TCHH. To be able to detect and correct bit errors at the air interface, GSM performs channel coding. This procedure is organized in two consecutive processes, block coding and convolutional coding. In block coding, the parameters describing the speech data are first subdivided into three classes, which define if the data is important, required, or unimportant for speech intelligibility. With convolutional coding, the information relevant to speech intelligibility is doubled with an arithmetical operation. That means a copy of the data is made so the data can be restored if necessary. This procedure allows to fully compensate bit error rates of up to 12.5% in the secured relevant data. Channel coding increases the bit rate necessary at the air interface from 13 to 22.8 kilobits per second.